This is a similar setup for shutter glasses. And what you need here is that near the display there will be an IR emitter or RF emitter that will sync the image to the sensor on the glasses. And the shutter glasses are mounted, and in order to generate a shielding from stray light, you would like to put here some kind of a black box so that you measure the as if the glasses are on your eye. Your eyes are actually generating so that you are so close to the lens that you don't see light coming behind the lens. And this is the purpose of this box, and you see a very funny or improvised box, cardboard box that I put in the lab down. And you see the glasses are going into these holes. And the photometer is measuring one time focused here, through here on the display, and another time is focused on the other eye. Here are the glasses mounted on the box. And here is what you get as a set of measurement in this case. One time you have the screen left, right, both in the white mode, and you measure the luminance and the color coordinates. Then you switch to black, white, white, black, black, black. You get all these measurements. Here you fill the table gradually, all the combinations of red, green, and blue with the other channel black. You can skip the ones that are grayed here. These are low measurements, and they don't serve a lot of purpose. But once you have the setup, you'll rather take it. Then, once you fill the table and you do the same to the right eye, you have a lot of information. Now, what do you do with this information? And here you have actually the different definitions. The top one is extinction ratio, meaning how much the direct light with the unwanted or unintended light ratio is. And I put here the formulas in all of them. And you see all the formulas have the white, black, 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 white, and black, black. And the extinction ratio is actually 1 over the crosstalk is 1 over the extinction ratio. So if you compare these two formulas, you see that they are just inversion of one to the other. Now, when you go from the left eye to the right eye, like from here to here, you should notice that whatever here is black-white, the notation here becomes white-black, meaning you have to mirror the indices. Obviously, if both black, the mirror is still black-black. But when you have black-white, it becomes white-black. So all the formulas that are here becomes the formulas here by inverting the index of black and white. What you see here as an example that we have this system, it's a very high extinction ratio. Any number above 100 is quite respectable. But in the ICDM, we are not supposed to say what it should be. We're supposed to say only how to measure. So you didn't hear what I said. Also above 50 to 1 is already good enough. This translates to 1 over a crosstalk of 2% or 5%. It's already good. 1%, very good. 0.2%, like you see here for the left and the right eye, 0.2%, 0.27% is very, very good extinction ratio. This means that if you have a white building on a black, on a dark background, or vice versa, and you look on the edge, you will not see a ghost edge. The edge will be sharp. And when you look in stereo mode, you will see the effect, the stereo effect very clear. Stereo contrast is by definition is the contrast of each channel average. Here is the example that I told you. I will come back to the average of the luminance of the two eyes. Linear luminance in this case is 23.50, and the geometrical mean is 23.46. So in this case, the difference is negligible. So that's kind of numerical justification to why we choose to use the average, the linear average. Now, luminance differences in this case is 11.7% between the two eyes. From different papers and experience, you don't want to have more than 25% difference between the two eyes. Now, there are papers that go back like 30 years ago that actually inspected what is the difference between binoculars you use in the field to look. And they saw that if you have 5 times transmission of one eye relative to the other, you're still okay with the binoculars. But with stereo, if you go over 60% roughly from some papers, experiments, then you start to lose the stereo effect totally. So these are kind of guidelines numbers, and again, I tell you just from papers and experience, but as part of, if I put the ICDM hat on my head, I should not tell you anything. Now, once you take all the color information that we measured earlier in the table, you see that the color differences between the two channels in this case are very small. This is the radius in the U prime V prime map. Always it's better to see it graphically. So you see here the triangles are from the right eye and the squares for the left eye, and the points are almost overlapping. And most people measure the white and they skip the black because it's faster, but in this case it's also there. This is the same information in the U prime V prime map, and this is when you take the glasses out and you measure the display directly, you can measure the transmission of the glasses. And actually, in this case, transmission of the left channel was 25 and the right 26%, and the average is 26% roughly, which is very high. And we measured other glasses that were much lower. So I'm already behind time, but I'm getting closer to the end. When you have a stereo, auto stereo, it's very important to know that the effect or the matching to the eye of the beam is only at a given distance, optimum distance, and actually at the optimum location, which we call usually sweet spot. But you can move around it, and what you see here, this diamond shape that you have here, shows how much you can move, and we call it the viewing range.